A quick recap of the program. So today we will probably finish the lecture on confidence intervals, and after that we'll do exercise session on the theory part. Tomorrow the lab will go on, but before the lab we'll do a test in class, and depending on what we did not do today in the lecture, we might or might not have a lecture tomorrow. We will see how fast we go today. So tomorrow at 1:15 sharp in this class we'll do a test, right, a written test. What did we see last week? We discussed confidence interval. If I have some data that I have obtained from a measurement and I want to summarize one of the metrics, I can summarize them with a median, and we have seen how to obtain some accuracy statement about what really this median means. And the hidden thought behind that is we assume that the median that we have computed from the data is an estimation, a noisy estimation of a true median that we would have if we would have access to all the hidden information that exists in the system. We can do the same for the mean. So if we estimate the mean of, if we compute the mean of the data, so if the data is just a number, the sum of the numbers divided by n, we can interpret it as a noisy estimation of the mean of a hidden distribution that we don't know, of course, and what we want is to quantify the accuracy about this mean, with the hope that if we have a small number of data points, we have less accuracy than if we have a large number of data points. How do we obtain such formulas? Here is the classical formula, the one that's captured in all statistical packages that you may use. It's based on the central limit theorem, as we will see. But let's see first what it says. So let's assume I have obtained n data points, single numbers. I call mu n hat the sample mean, so 1 over n the sum of the xi, and Sn is the sample, one of the estimates of the sample standard deviation. Sn square is therefore an estimate of the variance. A simple formula for the variance is to say it's 1 over n, sum of the xi minus the mean to the square. So it's the average of the distance to the mean square. This is Sn square, therefore Sn is the square root of all this. Then, the theorem says that if we assume that these data points that we have obtained are generated as n samples from a given distribution that has a finite mean and a finite variance. Many distributions have, not all distributions. You can have weird distributions that have infinite variance or infinite mean. If that happens, that doesn't work. If both are finite, then the theory of probability 101 says that if we rescale all of this, that means we take the sample mean, mu n hat, minus the true mean mu. The true mean mu, we don't know what it is because we don't know the distribution. That's what we're trying to infer. Divided by Sn, so Sn is the best we can say about the standard deviation. So if we do this, if I have a distribution, I take minus the mean, I obtain a center distribution that's centered around 0. If I divide by the standard deviation, I obtain a distribution that is in per units. The standard deviation of this one is 1. And I rescale by square root of n, I obtain something that, when n is large, will be approximately a distribution, which is the magic distribution, the Gaussian distribution, the normal distribution, regardless of the hidden distribution f that we don't know. So in some sense, the take-home message is when we average n things together, whatever the things come from, at the end we obtain, under those assumptions here, the normal distribution. This explains why the normal distribution is so important and so frequent. Since this is normally distributed, we can derive from that the confidence interval for the difference mu n hat minus mu. We know this is, roughly speaking, Gaussian with this Now, if we look into the table of the Gaussian distribution, for example, we find that with probability 95%, it is between minus 196 and plus 196. Therefore, we know that this thing here is with probability 95% between minus 196 and plus 196. If we do a bit of math to get what we want, which is what the difference here, that means the mu, the true mu, must lie between mu n hat, my estimated, plus or minus 196, then the scaling factor that we have here. This is how we use, this is the formula that is classically used to obtain something about the mean. Right? We will see in a minute how to use it practically, but a few observations. If we compare to the previous result we had about the median, we see this one is seemingly more simple. If we care only about applying formula, I can view this formula as something very simple-minded. If I want to apply it, what do I need to do? I need to compute those two quantities, decide on my confidence level, from which I get a magic number, 196, that corresponds with 5% uncertainty. And then I simply have this number here, where the number of samples plays by a square root of it. So it's very simple compared to confidence interval for the median, which is also simple, but requires a bit more computation, because for the median, what do we need to do to find a confidence interval?
Sort it and find the indexes.
Exactly. We need to sort the data and find, go into the table to find two indices, but those indices are useful only when we need to go back to the sorted data. So it's a bit more simple here. However, if you see, it's more elaborate in the sense that it relies on the convergence to the normal distribution, and it's true if n is large. So what does it mean for n to be large? We will come back to that in a second. Is 10 large? Is 30 large? Is 1 million large? We will see that it depends on a few things, and we'll see that in concrete cases, we're able to say whether n is large or not here. So for one of the examples we saw last week, we saw, well, here's a classical formula that you will see. I have obtained n data points. I have an estimate mu of the mean. And I need an estimate of the standard deviation, and this quantity gives me the width of the confidence interval, which is shown here in those values here. This is the red line is the mean. The dotted lines are the confidence intervals here. So we see that median or mean for this example doesn't make much difference, although the values obviously are different, but the results are the same here. Here is just in written form what I explained orally a minute ago. There is a second case which is often used and confused for that, and that explains some of the small details that are sometimes different. Sometimes in simple statistic book, not in sophisticated one, but we find this result. Assume that I have a data sequence x1, xn, and here I assume that this thing with common distribution n mu sigma square. So n mu sigma square, in this course I use this terminology, that means the normal distribution with mean mu and variance sigma square. So if I assume this, then I have some result. Let's discuss the assumption here. The assumption here means that the data I have received, I already assume it comes from a normal distribution. That's a strong assumption. If you measure the time to transfer a file, or the response of a web server, or the throughput of a protocol, it might or might not be normally distributed. It might be normally distributed, but usually this appears if this is the aggregation of many small independent things because of the central limit theorem. If you sum up lots of small independent random variables that have the same distribution, at the end you will find something that has the Gaussian distribution. But there are many things that are not in this case. So this theorem is to be used with a lot of caution and criticism. The previous theorem which gave practically the same result, but was not assuming that. It was just assuming n is large, and when we take the sample mean, then whatever the initial distribution, we will end up having something that looks Gaussian. So if we can assume that this is Gaussian, then the formulas are very similar, but are in fact stronger. So we do like before, we estimate the sample mean. We estimate the variance by 1 over n minus 1. Why do we do this? Not 1 over n. Because of the bias. What does the bias mean?
The expected value of that is different from the true value.
The expected value should be the true value. So sigma n square hat is a random quantity. I have observed my n data points, but I assume this is one sample of a random experiment. So when I compute the standard deviation estimate, this is random. If someone else would redo the experiment with slightly different outcome, it will have a different value of sigma n squared. Of course, we hope it's not so different, but it is a bit different. It's a random quantity. And if the x are Gaussian, we can do the maths and we can explicitly compute what is the expected value of this. This is a quadratic formula with respect to x. If I assume I know the mu and sigma square of x, it's a small exercise, and we will do that kind of exercises later today. We can compute what is the expectation of all that stuff. And if we put 1 over n, we will not find that the expectation is sigma square, but if we put 1 over n minus 1, we will find that the expectation is exactly sigma square. This is called an unbiased estimator. An estimator is a random quantity that we think is close to a fixed but unknown quantity that we don't know, but that we would like to estimate. The fixed but unknown quantity that we would like to estimate is sigma squared. In fact, we don't want to estimate it. We just need to estimate it. It's, again, one of those nuisance parameters that show up everywhere when we do statistics. We don't care really about it, but it shows up in the formula. Therefore, we need to estimate it. So this explains the 1 over n minus 1. Then the second thing is, if I do this rescaling, similar to the previous theorem, we have an exact theorem. We knew that when n is large, this is approximately Gaussian. But here we know that even if n is not large, we know exactly what is the distribution of that. It's called the student distribution. It's a distribution that is independent of the parameters mu and sigma that we would like to estimate. That's the key thing. It's called a pivot in statistics. Whenever we have random things and we want to say something about the hidden parameters, one of the tricks that we will see many times is to find a true or approximate pivot. A pivot is a random quantity we build based on the variables, based on the random observations, that, under some assumptions, has a distribution that is free of the parameters we want to estimate. In the previous case, if we did not assume Gaussian, we can say that the quantity in the previous theorem here, this quantity, is an approximate pivot. Whatever the distribution f, whatever the mean mu and sigma square, this has a distribution that's always the same, Gaussian 0, 1. But this is only approximate. If the random variables are Gaussian, we have a finer result that says it's exact, it's a student distribution with parameter n minus 1. I will do through the math of that. You can look up Wikipedia to find out what is the student distribution. Perhaps we'll come back to this when we do ANOVA a bit later. Therefore, if I can go to the table or the MATLAB function for student distribution and say with probability 95%, this quantity will be between minus eta and plus eta, and then the rest goes on as before. We can even do more if we want. We can find a confidence interval for the standard deviation, but we won't really use that much. Now, if n is large, or we think might be large, like n equal 100, in classical statistics, large is often 100 or zillions, like in data science today. If n is reasonably large, we have then two results. Assume if the data is Gaussian, I can use the exact formula, but by curiosity, I could compare to what the approximate formula gives, which is more robust, is true in any case. And here is the result. First, when we compute the sigma, we do 1/99 instead of 100, so there will be a small difference. And the second thing is the magic number eta that comes from the student distribution. Here will be, for confidence level 95%, will be 0.198. For confidence from the Gaussian distribution, it will be 0.196. Okay. So take-home message, if n is 100, student or Gaussian doesn't make a large difference. Remember, we're using that to find an estimate of the error margin. So we don't care about quantifying the error margin with 3 decimals. Right? So an accuracy of this or that is the same here. So concretely, this theorem is useful only when we are sure that the x is very Gaussian and n is small. If it's not small, the benefit is negligible. Which you can see here also, n is the index of the student distribution. If we look at the 95% or 975% confidence interval from Gaussian, we obtain 196. If we look at the value here, we see that with n equal 10, there is a significant, although already not very large, difference. And when n gets larger, as we saw, the difference becomes quickly negligible. Okay, that's the first thing we saw. That's very basic, and everybody uses it. And the trick is to use it right. Now let's go a bit beyond. Let's see a practical case where I would like to use this. Very frequently, this happens very frequently when we do something that may fail, and we want to estimate the probability of failure. So let me start with a simple case. I run the system 10,000 times, and I found 200 cases where it fails. So what is the failure? It might be lack of convergence of an optimal power flow algorithm. It could be failure due to consensus protocol not converging, etc. So we do 10,000 experiments, and we fail 200 times. What we want to estimate what is the failure probability. So a first immediate answer is 200 divided by 10,000. It gives me 2%. That's the failure rate that we have seen in our experiment. Now, can we quantify the uncertainty about that? Because if someone else had done the experiment, perhaps they would have found not 200, but 190, or perhaps 195, or this would be just due to the randomness of things. Let's see how we can cast that in the previous example. We can interpret that as the outcome of a random variable that's binary, 0 or 1. And if we call 0 the probability of, if we want to estimate, so 0 should be the probability of success, and 1, 0 should mean a success, and 1 a failure. So that if I take the expectation of xi, it will be p, the probability of failure. Right? P times 1 plus 1 minus p times 0. So in fact, estimating p is the same as estimating the mean. So we can apply the result we saw before. I can say that obviously the asymptotic theory applies because this is, well, we'll see exactly when it does apply. But this is a distribution that's very simple, 0, 1. It's not heavy tail. Doesn't take huge values once in a while. So we compute the sample variance by using the formula, 1 over n, sum of the xi minus the mean square. So mu n is this mean here. A little trick is this formula here. The variance is the mean of the square distance to the mean, right? But I'm sure you must have seen in your young ages formulas like the variance of a random variable, which is the expectation of x minus the mean of x squared, but is also the expectation of x squared minus the mean to the square. Right? This is a classical formula which you can show very simply here. Here, instead of expectation, I have sample mean, but the math goes exactly the same way. The mean of the difference square is the same as the mean of the square minus the square of the mean. Right. And now, xi squared is equal to xi, because xi is equal to 0 or 1. Right? So the mean of the square is also the mean. So this is mu n. So mu n minus mu n hat is my estimate of the variance here. So which I can compute here, 002 times 0.98, which is with 2 digits 002. So the standard deviation is approximately this, right? Square root of 2 divided by 10. So I can conclude that the confidence interval is this, eta 196 at confidence level 95%, multiplied by 0.14 divided by square root of that stuff, which gives a 0.03. So my probability of failure is 2%, but if I want to have a 95% confidence on it, I should say it's somewhere between 197 and 197 and 2.3%. 17, 0.17, so 1.7% and 2.3%. That's what I can say here. Very simple, no trick. No, that's very easy. Here comes the trick. I do the same thing, smaller number of times now, 10, but I see no failure. But I know the system can fail. And I would like to say something about the failure rate. Can I say something by having observed no failure? You can see the distribution of votes. Many say A, a few says E, F, and a large number says is cautious and say I don't know. A is what we obtain if we apply the formula, right? The sample mean is 0. The standard deviation is also 0, therefore it's 0, right? Which means we are 100% certain that this system will never fail. Of course, we can't believe in that. I mean, it's just because I've done so few attempts to make it fail that I've never saw it fail because the probability is small. Therefore, I conclude with certainty it will never fail. This is, of course, absurd, which means there must be something inaccurate in what we saw before. In fact, we are in a case where the central limit theorem here does not apply because n is too small compared to the probability of the rare event. If the probability of failure is very, very small, in order for the central limit theorem to apply, we need, it's a bit like in deep neural stuff, we need to see the thing several times. So we need to have a number of runs such that there is a good chance that you will see a few times the thing that you want to, the failure. Right? If the probability is so small that it's quite plausible that you never see it, unless you do zillions of trials, then of course the central limit theorem will not apply. In other words, for this specific distribution, we need a very large n. We will see for this specific example what large n mean here. But here it means, obviously, this should not be used. There is, fortunately, a special case for that, because that's a very, very frequent case. So statisticians or probabilists have thought about it, and there is a theorem for this one, which is not very much known, but is very useful. It's a very important thing. You will always be confronted with that problem. You will run your system, your algorithm, and it will converge whenever you did it, but you don't have a formal proof that it will converge, so you still want to ask questions like, how many trial runs should I do to be reasonably certain that it will, that I can estimate the probability of failure. Here is the answer. So I assume we have n independent experiments and we observe z successes. So z is an integer number. That's my data. I want to say what's the probability of success, what's a confidence interval for the probability of success having observed z. So we see we are in this classical statistical framework that we will use throughout the class, that is used practically always also in data science or in statistics. I assume that I have a hidden model. Here the hidden model is probability P. And I have some data that comes from the model, and I want to infer the hidden model from the data. We want to say something about Z. And we know that just finding an estimate, a point estimate of Z is not sufficient. We want to have some interval to quantify the answer. Here is the answer. The answer is, it is given by a lower and upper bound, L of Z and U of Z, that are both constructed symmetrically. So the upper bound is 1 minus the lower bound of n minus z. N is the number of data points. And the lower bound, L, is obtained by 0 if z is 0. Otherwise, it's obtained by this function, phi n z minus 1. What is phi? Was given by yet another formula. Phi n z is given by n1 and n2, where n1 and n2 are constructed from z and n. And f comes from the confidence interval, alpha. So if I want to be sure with probability 1 minus alpha, so gamma here is 1 minus alpha. And this is a distribution which is called the Fisher distribution with those parameters here. So where does that come from? I will not do the explanation, but it has to do, is very similar to how we computed the confidence interval for the median. For the median, we had Bernoulli trials. Here it's very similar, but we need to invert the CDF of the Bernoulli, and this is exactly phi n z is the inverse of the Bernoulli CDF. In particular, a case of interest is if we observe 0 success. We do n experiments and we observe 0 success. Then this formula has a closed form. We know a confidence interval is lower bound 0 and upper bound this formula, which is given by this 1 minus gamma, where gamma is the confidence interval, is 1 minus alpha, times over 2 times 1 over n. And if n is large, it's 1 over n times a constant here. Right. So that's the first thing we observe. Second, since we have a closed form expression for those things, or quasi-closed form expression, we can know when the normal approximation works, the one given by the standard way of computing confidence interval for the means. And we know practically it works whenever the number of positive outcome we have seen, or number of failures, is at least 6. So 6 is a magic number here. Or is at least n minus, is not more than n minus 6. Right? If we never see a failure, it's as difficult as if we always see a failure. So those are the conditions that tell us when n is large. Right? For a given z, the condition to apply the normal approximation, which are exactly those formulas, are the given one here. So the take-home message, at least sub-message, is that if we see no failure, then it doesn't mean the probability is 0, and we are certain it's 0. A lower bound is 0, but an upper bound is this formula here. And if n is large, and not very large, we can do linear approximation of this by using the power series expansion of the log of 1 minus epsilon. And we find this useful formula. P0 of n is approximately 3.689 divided by n. So we see that for large n, it decreases in 1 over n. If you want to have a confidence probability that is less than 10 to the minus 6, you need 4 million runs to be sure that your probability of failure is less than 1 in a million. So this is what the theory tells us. So it's a bit more sophisticated than simply saying, okay, I've done it 1,000 times. I've never seen a failure. How do I know whether I would have seen a failure in 1 million times here? Here it answers exactly this question. So let's return to our question of before. So if we apply the formula, we will find exactly this value, right, with a calculator, which is fairly large, right? If you during 10 times, so if you compare the naive answer we saw 15 minutes ago, well, the confidence interval is 0, 0. No, it's not 0, 0, it's 0, 1 out of 3. That's the only information you get by not failing 10 times. If we do it 10,000 times and we find 200 failures, the example I gave before, we had computed in a certain way, and here we can check that this formula that is given here is exactly the same as the classical formula for confidence interval for the mean. Okay. So take-home message, confidence interval for the means gives you a formula that is relying on some convergence to the central limit theorem, which very often is true, but there are corner cases where it's not true. Here is one corner case. It is when you're trying to estimate a probability that's very small, for example. For this, you can be a bit more careful and use another formula, but the good news is this is entirely solved. Theoretically, we know how to compute it here. So take-home message so far. Confidence interval for the median is easy to get. Requires IIDness, no other assumption. Confidence interval for the mean also required IIDness. And of course, it's trivial if the data sample is normal or if it's not heavy-tailed and n is large enough. Right? And when we have a success probability, we can have, or failure probability, we can use those special formulas. Now let's discuss a bit about this number of things we've done. The confidence intervals that we have, and the only ones I know, they all invariably assume that the data we have come from an ID model, right? How do I know this is whether this is true? Well, we have seen last week that there are things that might not make it true. The example is if you measure the throughput of your mobile and you've picked the Huawei versus the Samsung, and one has a small socket buffer size, the other has a large socket buffer size, and they're not ID because they don't come from the same model. Right? So hidden factors might prevent you from making the thing ID. So you should look for hidden factors and randomize them so that you can believe that the things you're doing are truly IID here. So that's what we call controlled experiments. When we do simulation, then it's up to us. Then it's easier. When we do simulation, we have to make sure that we don't ourselves introduce hidden factors, but that's typically easier. Else, sometimes we don't know. We will see when we talk about tests, how to test the hypothesis that the data is really independent. Typically, we will find that when we have zillions of data, they are not always independent. So we will need to do things like subsampling or other techniques for computing confidence intervals. Right? But right now, the first important thing is to develop an intuition for what happens when the data sample is not independent. Right? We have seen examples with hidden factors. Imagine another example where you measure something and you take many measurements and you introduce an error, and the error is due to the instrument, or in old days of physics, it was called the personal equation. In old days of physics, you would measure things by looking through something and seeing where the number is, so analog science. And if you look a little on the side or on the left, right, you will do a parallax error. And people tend to do them systematically. Each of us is not truly symmetric. When we believe we do things right in the middle, we're always a bit left, always a bit right. The physicists call it the personal equation. Personal equation means that the measurement errors might come from a hidden factor, which is how the guy who measures things behaves, or how the instrument has a bias. And the result of that is that different measurement errors are positively correlated. If you tend to read a bit more, you will always read a bit more, all right? So what happens when we have positively correlated measurements? Then we have less information than when the measurements are independent. Right? Because if things are positively correlated, the second value is related to the first one. In fact, the first one is a better prediction of the second one. If they are negatively correlated, that's the opposite. Negative correlation means if one value is less than the typical value, less than the mean, the next is more likely to be larger than the mean. That happens also in some measurement errors. Typically, for example, if you count the money, if you are a shopkeeper like Joe in the first lab, and you count for the money, that at the end of the day you count the money that's in your bag. Some of you worked at keeping a shop or an office of some kind. You do the accounting of all the things you've sold. You compare the money that's in your box that should match. Of course, it never matches because you do mistakes when you give money, etc. But if you do an error today and you take the same box of money tomorrow, the error will compensate. If you put too much money today, you start the following day with an excess that corresponds to the money you had the day before. So an excess one day will be translated into a default the next day. So you have negatively correlated errors. Well, that's good. Negatively correlated errors are good because, in fact, they tend to be erring on the wrong side. The thing that is misleading is this one. If I have positively correlated measurements, they give less information than 10 independent measurements. Right? And if they are giving less information, that means that the confidence interval, if I am computing the confidence interval, ignoring the fact that they are positively correlated, what error am I doing? Am I overestimating the confidence interval or underestimating it? I am underestimating, exactly. If I have 10 positively correlated measurements, it's like not having 10 but only 2 or 3, because of the fact the second one is repeating much of the first, etc. So the 1 over square root of n that I have is exaggerated. We will see when we talk about time series, there are, in some simple cases, we can quantify this exactly. But the first thing to remember here is if our measurements are not IID, and if I compute confidence intervals or prediction intervals that we'll discuss in a minute, assuming they would be IID, I am being overly optimistic. Things are worse than there is more uncertainty than I really believe. Something important to keep in mind. Sometimes we will have very small positive correlation, in which case we will keep the formulas and just know we're making an error on the optimistic side. But sometimes that means we should not use formulas for confidence interval. Yes, question?
Just because we are underestimating the means, this is the reason why we will be underestimating the confidence interval. It is
the variance of the sample mean, exactly, yes. The variance of the sample mean will have to do with the autocovariance matrix of all the x, and depending on whether it is a positive, there is positive correlation or negative correlation, this will give me less or more than 1, which is what we assume when it's independent. We'll come back to these computations in a few weeks. Another reflection, what does it mean that things are independent? It's important to be able to reason about it without having to formally demonstrate it. When I'm doing a simulation in particular, I want to be reasonably sure that the outputs that I give are independent. In a simulation, it's easy. So first question, what does it mean exactly, independence? We have a perfect tie between E, F, G. So E, A and C, F, B and C, and O. Well, let's discuss. I mean, it seems that all are true. So certainly C is true. That's one form of the definition of independence. Having observed x1, xn minus 1, this is the probability I can attribute to xn. And if they are independent, it means that this does not depend on what I have observed here. Right. Which is about the same as A. Now, of course, it depends what exactly we mean, so all answers are valid. But the important thing or the apparent paradox is to say, if I tell you I have observed 10 times the value of something, and now I will produce an 11th value, and they all come from the same distribution. I can't say something about the 11th value, right? What can I say? Well, I can estimate the mean of the 10 I have obtained, and I would say the 11th one, if I have to bet on something, I would say, well, it's close to the mean. Of course, it might not be true. There will be a distribution, so if I want to do a bit better, I can do what we call a prediction interval that we will give in a second. But here, what we can say that if we know the data comes from an IID sample, by observing n samples, we gain some information about the distribution, which will help us gaining some information about the next one. So the correct statement about independence is for an observer who knows the distribution, revealing previous values gives no information about future values. That's the true definition of independence, right? So there is this subtlety here. When you reason about whether your simulation is producing independent outputs, you have to assume you are an observer who sees the output of your program and knows your program, in fact, but doesn't know the random number generator. We will see next week how that simulations are always deterministic programs that transform an output of the random number generator. Knowing the distribution is knowing the program. But we assume if a random number generator is a good random number generator, it's impossible to infer what the next values will be, having observed the previous values. So that's the correct way of reasoning about whether your system is producing independent outputs. It is whether for somebody who knows the program but doesn't know what value the random generator will give, then the next value is not, there's no point having seen the previous values to find some information about the next. Voila, we do a break and we resume in 15 minutes. I forgot to add that tomorrow for the tests, obviously we will give to you the exam booklet. So you don't need to learn by heart all the formulas that I'm giving here.